Hi guys, we're going to take a look at your repeated measures ANOVA assignment, also known as RMANOVA for short. And no difference in the Jamovi modules that we're going to use. I went ahead and left all the modules that we've used for the semester and instructions about how to load them on there. We're going to go ahead through our steps of data preparation before we analyze the data files. We're going to check for accuracy with some of these elements that we have listed, missing data and outliers, and then once we do that, we'll move on to some statistical assumptions. So I already have Jamovi open with this data set from field called Bush-Tucker. Doesn't sound like a great show. Go ahead and read through that chapter and he'll describe the data set for you, but it's some Australian show that he used an example of people eating different gross foods and them getting sick from them. So we'll go ahead and let's look at the data portion in Jamovi, and we can double click on the column header to see the first variable, and this one is an ID variable for people. You'll notice this only has 8 participants and 4 different variables, and these are different animals. One was an insect, one was a kangaroo, I think, one was a fisheye, and I don't remember what the last one was, some other animal. So one thing to note about repeated measures designs, the upside of those designs is that you need a lot fewer participants to get statistical power. So you can recruit fewer people. And in this case, the other advantage of these types of designs is that people basically can be their own controls for a study. So if they experience each of the study conditions and you're measuring the same people, then you don't really have to have a control group because they are their own controls. And there's some different ways you can organize those types of studies, like randomizing what order you give them different study conditions and things like that, because there are some issues with the same people receiving successive different treatments. So besides different treatments, the other common design you'll see is measuring the same people over time. If you're looking at some kind of time-related phenomena, things that, drug effectiveness or weight gain or weight loss or things like that happen over time, and you might measure in successive weeks or months, and it might be the same subject. So those also might be repeated measures designs. This first variable is an ID variable. Again, Jamovi has an ID data type, so we'll go ahead and make it that. And these others are all going to be continuous measurements, and you can read in there what he's actually measuring, but they're all going to be continuous variables, and that's what they come up as in Jamovi. We'll leave it when we opened up the SPSS data set. We can look at this and see all the variables and rows, and we know there aren't any missing data. Nothing seems to be amiss, but if we did have a large data set with a lot of variables and a lot of rows, then we'd want to go look at our descriptive statistics. So we're going to go into descriptives, and these are all continuous variables. If we had a categorical variable, then the appropriate descriptive statistic would be frequency table with frequencies and percents, and the plot we'd want to look at for those would be a bar plot. But these are all continuous, so we're going to go move each of them. Oops, I'm going to hit Shift and select all the variables and move them over to the variables box. And under statistics, we'll get means and standard deviations. We might look at the skewness for each variable. Go ahead and get our normality tests for each variable. These are parametric tests. We do care about if our normality of the variable in the population. That'll give us the basics. And for plots, so the descriptive statistic for continuous variables are means and standard deviation. You pretty much should have that memorized by now. And the appropriate plots should be a histogram and a box plot. And those are the best plots for descriptive statistics, or for data exploration with continuous variables. And as we noted, 8 participants in each variable, no missing data. We do have some different means, and I think it was length of time to get sick, so some of those were lower than others. Skewness divided by standard error. The skewness, we would be concerned if that value was greater than 2, and none of these look like they have that issue. We can see our histograms and box plots, and none of them are not looking too normally distributed, but it is low sample size, so none of them are going to be. Stick is probably the closest to a normal distribution that there is, but nothing statistically significant with our Shapiro-Wilk test, so we're good enough. Well, not perfect, we're good enough to go look at this. So for our statistical assumptions, we still, while each participant was looked at each study condition, the different rows, the different participants are independent of each other. We still have that assumption. The sampling distribution is normally distributed for each group in the independent variable. And maybe I should restate that. Let's change it to this time pointer study condition. If we had an additional independent variable, we would still have our homogeneity categorical variable. We'd still have our homogeneity variance assumption. We're not going to get into that level of complexity with repeated measure ANOVA. Be aware that you can have independent variables that are categorical, and it does add an extra level of complexity that we're just not going to get into. And we have a new assumption called sphericity. And what sphericity is when you have your different study conditions or different time points, we are looking at the difference between pairwise groupings of those study conditions or time points, and comparing those with pairwise groupings of the other study conditions, and the variance of the differences are supposed to be equal. So it's very similar to homogeneity variance, but we're not looking at the actual variance in each variable. We're looking at differences between sets of 2 variables, and to see if those variances and the differences are the same. And that's not something that we can look at here with descriptive statistics, but there is a test that we will look at when we get into our repeated measures ANOVA, called the Mauchly's test of sphericity. And you should note that if you only have 2 time points, you can still conduct your repeated measures ANOVA, but you will be unable to test your sphericity assumption because there's only 2 time points, which gives you 1 difference, and there's nothing else to compare it to. So in our example from the field text, we have 4 different study conditions, and those would be the pairwise comparisons between all the combinations of those that we could test. So if you only have 2 time points, you cannot get a sphericity test. Okay, so that's about all we can look at this point. So we will continue on and go ahead and I put the steps in here to check in StatCat what should be tested. We can just take a quick look at that. Go to StatCat, repeated measurements, and our related variables are these 4. And you'll see when we put that in, we do get a suggestion of repeated measures ANOVA. And if we had a problem meeting our normality assumption, there is a non-parametric Friedman test that could be done for a one-way repeated measures ANOVA. We're not going to look at that. In fact, I've never conducted that test before, but I'm sure it'd be pretty straightforward to conduct. So now that we've looked at that, we can go look at our repeated measures ANOVA and continue on with our process. We're going to go to ANOVA, and in our analysis section, ANOVA and repeated measures ANOVA. And you'll see we have factors that we can have in here. And we're only going to have one factor, but we're going to have levels of the factor. And each of these variables are going to be a level in that factor. And it gives us 2. We actually need to have 4. So we're going to, if you double click and hit enter on the 3rd level, you get 1. And if you go into the 4th one and enter again, and now we have 4 variables there. And you'll see under repeated measures cells that now we have 4 variables there, and you can drag them over. Well, let's just select them all. Oh, that worked. So select them all and drag them over, and you'll see that it puts 1 variable into each of our levels. And this is called a within subjects factor in SPSS. I kind of like that terminology. So we know that these are the same subjects and they've done all 4 of these tests. We could include a between subjects factor, and like I said, it starts to make, and we could include covariates. I mean, it really can get complicated, and we're not going to go into that level of detail with repeated measures ANOVA. So beyond the scope of this course. So we can already see we have some results there. I'm going to go ahead and get our partial eta squared because we can get that here. The model is already set up for us. That we have our repeated measures components. We already said we weren't going to get any between subjects, so we're not going to make any changes in the model section. Assumption checks. You'll notice that we have a new one for sphericity. We want to get that assumption check. And we're going to go ahead and look at a couple of other sphericity corrections, the greenhouse geyser and the Hunfelt. We don't have a categorical variable in this test, so Leavings isn't going to tell us anything. And if we look at it, we'll actually see that because there's no categorical variable, there's no results in the output there. So if we had a categorical variable, we would definitely check homogeneity variance with our Leavings test, but we're not going to do that here. We'll go ahead and look at this post hoc test, and we'll talk a little bit more about that in a little bit. And we'll leave that with Tukey. We do want to get in the estimated marginal mean section and drag the repeated measure factor 1 into the term 1 box under marginal means, and we will go ahead and get our marginal means tables, and we can leave that error bars on confidence interval. And under options, we'll go ahead and click on group summary and see what it gives us. Okay, so Field has a pretty nice discussion in a couple places about repeated measures ANOVA and sphericity and these greenhouse, geyser, and Hunfeld adjustments. So the first thing we probably want to go look at is down here under our assumptions, our test of sphericity. And this is called Mauchly's test. And we're looking at our p-value, and we see that it is under 0.05, which means our sphericity is, our assumption is violated somewhat. And then we have a greenhouse geyser correction and a Hunfeld correction. And Field, and I think he's probably pretty right about this, basically says you could probably ignore the result on your Mauchly's test and always get a greenhouse geyser and Hunfeld correction, and just look at the results for those corrections rather than look at the uncorrected result. Unless, and the cool thing about these corrections is they're really dependent on how much you violate your sphericity assumption. One of the downsides of this Mauchly's test is it is affected by sample size. So if you have a very large sample, any small deviation from sphericity will make this result significant. And if you have a small sample, even large deviations from sphericity, the result may not be significant. And so his argument is that because this actual test is so sensitive to the sample size, you may as well go ahead and get these correction factors and the results for them, because they really depend on by how much you violate your sphericity assumption. So they're always going to be calculated to kind of tailor fit to your particular test. So there's really not a reason to look at the uncorrected version because this is going to give the correction that's probably appropriate. And he also has a little more discussion in there about that the greenhouse geyser might be a little bit too conservative in how much it corrects, and the Hunfeld might be a little bit too liberal with how much it corrects, and the correct answer is probably somewhere in between these two. So this really is a test where you kind of have to I guess give up your black and white thinking and kind of get a feel for what the results may be telling you. So we're going to go ahead and look at our greenhouse geyser line here, and do note that what gets adjusted is the degrees of freedom. And what happens is it takes your uncorrected degrees of freedom, multiplies that by your correction factor that was down here in your assumptions table for sphericity, and then multiplies that and gives you the result of that different change in degrees of freedom. So you'll see that our sum of squares, there's no changes in any of those. The degrees of freedom, they do change based on our correction factors. Our mean squares are different because the degrees of freedom were different. And then the F pretty much remains unchanged, but the p-values do change. So under greenhouse geyser, we see that our p-value is greater than 0.05. Under the Hunfeld, it's slightly less than 0.05. And Field makes the point that, you know, these two do not differ by much at all, and yet one would be considered significant and one not. So you really kind of have to go look at these groups and what it looks like is going on with them. But there's really not a huge difference in them. And we do have our model information for degrees of freedom and mean squares, and our residual which will be important when we look at our results and report them. So Field has a good discussion that when you violate sphericity, that it causes problems for your post hoc tests. And so these post hoc tests are comparing the different levels of our variables, our 4 different levels, and we do get a test, but this is a 2-key correction, which is kind of a middle-of-the-road correction. And since we did violate our sphericity assumption somewhat, these results are not exactly accurate. And so the post hoc tests are probably not where we want to go for violating our sphericity assumption and have a pretty decent greenhouse geyser and Hunfeld correction like we do here. And also note that these are both less than 1. If you met your sphericity assumption all the way, then these numbers would be 1. And what that would mean is that there is no change to your degrees of freedom. And so, again, just another reason why it's probably wise just to always get the greenhouse geyser and Hunfeld and report those results. Because if there's no violation of sphericity, it will give you the exact same answers, no corrections. So we're going to go look at our estimated marginal means information. And we can see here that, and unfortunately, it does take our level and doesn't give us the names of our variables, but it has the level 1, 2, 3, and 4. So to understand that, you would need to go back to your original data and look and see what is level 1, and that was an insect. Level 2 was something else. Level 3 was fisheye, and level 4 was something else. I can't remember what that was, something Australian. And we do see some differences in these groups. And we do have the means and standard errors here. And I think what's useful to look at, and I did select the confidence intervals, and when there is a on the error bars here, I left the confidence interval selected. And even when there's a significant difference between groups, you will get a little bit of overlap in your confidence intervals. But if you don't have an overlap, it does say that one group and another is quite a bit different from each other. So if we looked at level 1, we see that goes from 6.33 to 9.92. Level 2, 2.45 to 6.05. You'll see those confidence intervals don't actually overlap with each other. So there is a good bit of difference between the level 1 and level 2. If we look at level 2 and 3, those are the confidence intervals there are pretty close to each other. They almost totally overlap. And again, 1 and 3 do not overlap with each other. And then you'll see level 4 overlaps with both the other levels and level 1. So there's probably not a significant difference there. So this test is a little bit inconclusive because of our the similarity in our greenhouse geyser and our Hunfeld. And I would probably report what our greenhouse geyser levels were, and you could potentially report means for your 4 different groups, and that would probably be sufficient. We're not going to get into a lot of analyses using repeated measures ANOVA, so this is kind of an introduction. If you want to know more about it, then read through the field text more extensively, because we're going to move on from here to other tests. So we would want to go through our steps on our answer sheet for doing our null hypothesis significance testing. So the null and alternative hypotheses for our repeated measures in ANOVA. The null would be There is no difference in the means of our treatment conditions or time points depending on which type of design you're doing. The alternative would be there is a difference. Our criteria for rejection that we're going to stick with for this class is alpha equal 0.05. We calculated our test statistic using Jamovi, and I would probably report that we failed to reject the null, reporting the greenhouse geyser correction information, and say that there isn't a significant difference. But I probably would highlight that there are a couple groups which do differ from each other. And you can see in Field how he reports that. On our answer sheet, I would, so under the Statistical Assumptions, Part 2D here, you do want to list out the assumptions for this test. And obviously we have our new assumption of sphericity, which we do violate somewhat because we have a Hunfeld and a greenhouse geyser correction, which is less than 1. And I would report those as an issue in this test. You can fill in the alpha level, what steps you took in Jamovi to fill this test in, and I would fail to reject and give the meaning of the result that there's not a significant difference between our groups, but we did note a couple different groups that did differ from each other. That was the level 1 and level 2 and level 1 and level 3 that did not overlap in their confidence intervals. We're not going to really do any follow-ups other than looking at the marginal means and looking at those confidence intervals. That was our follow-up. I would report the greenhouse geyser. You could report the Hunfeld too. And in this main effect, I would probably call it like a study condition and then list out what the study conditions were. Sometimes you're looking at time points, in which case you could name that, time and, and then what time points you measured things. Field did not mention this much, but if you're looking at time points, all of the study participants, all of the subsequent time points should be equidistant from each other with repeated measures ANOVA. So say you measured these 1 week apart at each time point or 1 month apart at each time point, but the time points should be consistent for the different study participants. If they're not, then you will run into some problems, and you'll need to do a little more sophisticated analysis of that, which is beyond the scope of this course. And we would report our F statistic from our table up here, and I would report the information from the greenhouse geyser line. So our F would be 3.79, our degrees of freedom for the model would be 1.6, and for the residual would be 11.19, P equal 0.063, and a partial eta squared of 0.351, which is still a pretty decent effect size. So even though this is probably a little bit of an underpowered study, that effect size for a partial eta squared is a pretty big effect. And Field makes the point that you probably want to focus a little more on the effect size than on just the straight p-value. And then you can give feedback and save your answer sheet and your Jamovi OMV file and turn those in for your repeated measures assignment. And I hope you have a good week, and I will see you in office hours.